So in the last couple of minutes, we will just briefly talk about, well, if you do have dislocations, if you can calculate this, and if you, for example, compare metals with ionic crystals, why do they in general have very different mechanical behavior? And again, everything is related to the way or how easily dislocations will propagate throughout the material. So we learned already that metals are plastic, that they can be deformed plastically. What that means is that if you look at the stress-strain curve for metals, if this was stress and strain, they will have the linear or the elastic region, and then they will plastically deform. Eventually, they will break, right? But dislocations in metals easily move. And the reason why they easily move is, for example, usually there are FCC or BCC crystals, etc., but also bonding is not directional. So in general, they can be really plastically deformed. They're very ductile. So covalent ceramic materials, in these materials, the dislocation or the motion is very difficult. This can be due to both to the symmetry of the crystals, but also it's in large part due to the fact that the bonding is directional. So, in contrast to metals, how the ceramic materials will behave is that they will behave, they will deform elastically, but they will break. So there won't be any plastic part of this curve, stress-strain curve, right? So they will slightly expand or they will elastically change when you apply a stress, but they won't plastically deform before they break. So this is a major difference between metals, for example, and ceramic materials, and everything is due to how dislocations behave in these materials. And again, everything boils down to bonding and the symmetry within the materials, etc. Finally, the ionic crystals, in addition to directional bonding, also have charge effects. So, for example, for dislocations to move, you also have to account the fact that there are different ions here and that you have to overcome potential barrier that is simply due to Coulombic type of interactions. And in these materials, dislocations cannot move even further. So there are, for example, many semiconducting materials that are used in technology right now, gallium nitride, gallium arsenide, etc., where dislocations are very easily introduced during the growth, but it's almost impossible to remove them from the material once they are formed, right? And that's really comes from the fact that they have different type of bonding where the dislocation movement is more difficult. Okay, so in the last minute or so, I will just repeat what we mentioned so far, is that the mechanical resistance of a crystal is directly related to the ease of generating and moving dislocations. And we learned so far how they are formed and how they are moving throughout the material. So if you know the symmetry, you can calculate the slip systems, so you can predict how the material will behave. But one very important consequence of this analysis is that you can prevent this movement, or you can modulate, you can enhance it, right? And next time what we will learn is how exactly do you do that? So for example, how do you strengthen the material? For example, how do you prevent slip of the dislocations? So we will learn that there are different mechanisms of how this happens, but the first one is adding more dislocations. So for example, you have a material, it contains certain density of dislocations, and you want to strengthen that material. The way how you can do it, you can introduce more dislocations. How would you do that? Cold work. So you just deform it more and more. So this is called cold work. We will also see that you can do alloying by and you form a solid solution. In other words, you can introduce different types of impurities that will prevent the dislocation motion. You can form precipitates, or you can form different types of grains. Okay? You can change the size of the grains, their orientation, etc. And again, there is an entire subfield of material science where people study how by changing the size and the orientation of the grains, you can change the mechanical properties of materials. It's a very prominent and very important part of the material science. Okay, so with this, I will just summarize. So what we learned today is that we learned about two major descriptors that describe dislocations. One was tangent vector. The other was Berger's vector. So together, they determine whether the dislocation is edge, screw, or mixed. We also learned about Schmidt's law. And we also alluded to the fact that the materials can be strengthened. So next time we will learn more details about the strengthening mechanism, and I will give you a couple of examples how this is technologically relevant.